All right, looks like the new joins have slowed to a trickle, so I will go ahead and kick us off. Hello and welcome for joining everyone for today's workshop on an intro to formal verification. My name is Kelly Olson. I work at Supranational, a company where we focus on hardware and software acceleration of cryptography and other algorithms. I'm pleased to be joined by Joey, Giuliano, and Mark from Galois today, who will be running today's workshop. And for those that don't know, Galois is a company that's focused on using the most recent tools in math and computer science to advance the state of art in software and hardware trustworthiness. Today, we're going to be talking about a project that we recently started on, which is an effort to formalize BLAST, which is a BLS signature library that's designed to be compliant with the IETF specification for BLS signatures. This library is currently being used by both the Ethereum 2 and Filecoin protocols. And I'd like to extend a thanks to both the Ethereum Foundation and Protocol Labs, who have really generously supported this open source work in an effort to improve the performance and security in the blockchain ecosystem. So with that introduction out of the way, I'll pass it off to Joey, who will introduce himself and the team and kick off the workshop. This will be an interactive workshop. So if you'd like to ask questions on the voice chat, or type them into the chat box, please feel free to do that at any point. Thanks, everyone.
Thanks, Kelly. Yeah, again, please ask questions as they come to you. The familiarity of this crowd is not, we don't know what you all know going in, so we've got a plan. But if you find something interesting, we would love nothing more than to do a deeper dive into that. So ask in the chat, or I think even popping in on voice for a group of this size would be reasonable. So I'm Joey Dodds. I'm a principal researcher at Galois. I'm joined by Giuliano Losa and Mark Saltink, who are proof engineers with Galois, research engineers, but in this case, doing proofs. And we're going to talk about SAW, Kryptol, and this BLAST library. So SAW and Kryptol are the tools that we're using to do this formal verification of BLAST. So when we talk about SAW, we're talking about symbolic execution of LLVM, x86, Java, and Kryptol. The idea is that we take these implementations, we make functional mathematical representations of those, and then we try to prove equivalence between them. In particular, Kryptol is a language that we like to use for specification, so it's a pretty natural language for writing down cryptography and mathematical properties. It's got some features such as integers that are sort of unbounded representations of integers where you don't need to worry about the representations, as well as arbitrarily sized bit vectors that let us draw connections between implementations that we see in a library like BLAST and representations and higher level representations of numbers. So along with functional correctness, which is kind of what I just mentioned, we also can prove safety of implementations. And in most cases, safety means freedom from undefined behavior, and we'll get into that in a minute. So the idea behind symbolic execution is basically, at the very high level view, is that we treat memory and parameters of a program as variables rather than concrete. And so this is a really simple illustration of how we might think of something. Normally, when you're executing a program, we have a bunch of memory cells and we have a bunch of values that live in those memory cells. In symbolic execution, instead of all of those being concrete, we would have these values would be numbers. We treat them as variables. And sort of if we pass these through a program that increments things, we'll see that those variables were updated symbolically. So the whole idea of symbolic execution is more or less run a program as you would normally run it, but run it symbolically. So use variables in all of these locations and track the relationship between the program inputs and outputs, where inputs are going to be some combination of parameters and memory locations, and outputs will be returns as well as memory. So when we talk about safety, we're going to talk about this with regards to C in particular, because that's what we're verifying, as well as x86. The main thing that we mean is freedom from undefined behavior. So the C standard is large and complex. If you've had much experience with it, you know how many details there are. Freedom from undefined behavior, among other things, means that there are no buffer overflows, no null pointer dereferences, no signed overflows, and a whole host of other things that are built into the tool. What the tool does is it sort of automatically does all of these checks and makes sure that these things just cannot occur. If they do occur, we would be unable to produce a proof at all. We also do safety for x86, although the meaning of safety for x86 is a little less obvious because there's less of a concrete specification of what you're allowed to do and what you're not allowed to do in x86.
Yeah, I was going to ask about that. So that might include things like conformance to an ABI if you're trying to mix assembly code with C code. Is that right?
Yeah, exactly. So the boundary between C code and assembly code is, of course, a risky one. There's no definition of what you're allowed to do and what you're not allowed to do in assembly, but there are things that assembly can do that will ruin your day in C land. And so when we talk about safety in x86, it is about conforming to the ABI. I think we could prove code at a variety of different ABIs. Right now, we're focused on the ELF format and the Linux ABI. And we also enforce the C memory expectations on x86 in this case. So we more or less treat the memory as memory in C. And if, for example, x86 reads across the boundary of an ALEC block, we consider that to be an error for these purposes. Other things that we check are that memory that we've defined as const in C is treated as const by x86. This prevents, while there might not be a bug if one of these things goes wrong, or you might not observe a bug, this prevents sort of bad compiler optimizations or compiler optimizations that have certain expectations from ruining your day later on. So we treat x86 more or less as something that's tinkering with C memory, although of course x86 does do some things that C would not be allowed to do as long as they're not externally visible to C. We treat that as fine. And more or less, safety is extra important for libraries like BLAST. If you spent much time doing C programming, you know the fear of taking on a dependency, where if there's a memory safety problem internally in a library, that can have really bad consequences on the external code. And moreover, it can be really hard to narrow down where those problems are coming from. So for a library like BLAST, it's particularly important to make sure that if you take that on as a dependency, that you're not going to see any of these strange effects on the outcome of your code. So I think this is a pretty critical, safety in particular is important here. So unless there's any questions about the high level of what we're doing, I'm going to dive into a demo. We're going to prove an implementation of pop count. And if you're not familiar with the problem of pop count, what we're doing there is we're taking in a 32-bit integer in, and the goal is is the code large enough? I've made it, I believe, big enough to read.
Yeah, it looks readable for me.
Cool. So this is a specification implementation of pop count. And so this is kind of a slow version of this function, but the idea is that we're supposed to be able to believe that it's doing the right thing. It takes in a 32-bit integer that we call x. And what it's going to do is it's going to count the number of set bits in that 32-bit integer. So this pop thing is just a counter. We have a mask that we set to 1. And basically we sort of step through the 32 bits, incrementing our I. And then we mask off all but 1 bit, and we see if we have a value of 1 that results, and we just increment our pop. So this is sort of meant to be the most understandable version of this. I believe it also works if you sort of do other approaches. And then we have this is the heavily optimized version. So what we're trying to show with this is that one of the ways that we use SAW is to gain trust in optimizations that don't necessarily visually seem obvious, right? Here we have a implementation of pop count that we have reason to believe is correct. We've read it from a book and we've implemented it. But it would be nice to gain additional assurance that it's actually doing the same as what we would believe our sort of more visually obvious version is. So in this case, we do formal verification without using Kryptol, which is that specification language we mentioned. But we write a property that basically asserts the equivalence. We write a program that will return one if and only if those two implementations are the same. And so basically what we're going to do here is we're going to use SAW to set this X, as we mentioned, to treat this X as a variable. So what we're going to do is we're going to use SAW to symbolically check that for all possible inputs, this thing returns 1. And so if we go over to pop.saw here, we can see approximately what a SAW script looks like. We have some helpers that are just sort of notational things. We actually import, instead of the C file, we import a bitcode file. So we compile this C into LLVM. This is the LLVM intermediate representation, and that's what we load in here. And then you can see we treat X as a 32-bit symbolic variable. So we take that thing, we create it, we call it X. This is now a variable name. It has no concrete value. We're going to execute the function with X as this parameter. So this is just lining up just like a function call. And we're going to say, we're trying to prove that this function always returns true under this condition. So if there was a single case where it did not return true, the tool would complain.
So I guess using LLVM, if there's a bug in the compilation of the optimized code, then that's good because you'll find it. If there's a bug in the optimization of the simple code, then that's bad because you're not testing against the thing you wanted to test against. Pluses and minuses.
Yeah, exactly. So there's one layer of the compilation that we don't need to trust, in the sense of we don't need to believe the pass that takes us from C to LLVM is correct. But yes, of course, we could actually turn incorrect C code into correct LLVM code, and there are examples of undefined behavior that becomes defined in the pass between C and LLVM. So the proof is the most valid for code that is passed through the same compilation pass. Another way to word this, though, is that if you trust the compilers, if you largely believe that LLVM is doing the right thing, or that Clang is doing the right thing, then, and that GCC is doing the right thing, that these proofs will hold. Of course, they're not often, and I think we've actually just seen an example of the passes between this intermediate representation. In BLAST, we've actually just recently, I think, found an example of a compiler bug between the LLVM and the x86 that could still introduce a bug. So in general, the thing to get at here is that verification proves a lot, but it's always about pushing assurance out into more well-defined places. So one of the things that we treat as very important is to explain exactly what we've proved and what we haven't proved. So questions like that are great. And it's really important to understand exactly where the risk still lies even after verification is completed. And so then we say we're going to call this, this is a specification. At this point, we haven't tied this to a function. This is the actual verify command. It tells us that we're going to verify this pop spec check function with our pop is okay spec. And so we can just do saw pop.saw, and it will do the symbolic execution. It'll do the verification, and it will tell us that the proof has succeeded. So in this case, we have the property that things succeed. Here's actually an implementation that we've intentionally broken at sort of a very specific case. So it would be reasonably hard.
Quick question, how did it do that? I mean, that seems not quite obvious how you prove equivalence there. Did it like decompose the variable into bits, or how can it find that these two are equivalent? Like,
yeah, that's a
if I write them down as a formula, I probably get quite a complex formula that needs a lot of reduction to show that it's equivalent.
Yeah, that's the hard part of doing proof engineering. And so when Giuliano and Mark speak, they'll get a little more into the weeds on what we're doing with this for BLAST. In this case, yeah, we have a SAW works by having a model of LLVM that it maps all the way down to the bit level when needed. And we take these formulas, we do a bunch of simplifications in our tools before we hand them off. And at the end of the day, we pass these off to Smt Solvers to discharge goals for us. Smt Solvers, if you're not familiar, you can think of as more or less math engines. They take in math goals, and hopefully their sort of stated goal is given a formula, a predicate, give me an assignment of variables that satisfies the predicate. So this is an NP complete problem. It's a very hard problem in general, but the key insight of Smt Solvers is that we generally don't pass it arbitrary problems. We pass it reasonably well-structured problems that where there's often some insight and some number of rules that can be used to solve things. In this case, in a 32-bit integer, I'm not actually sure how the Smt solver is working to solve this problem. It's entirely possible that there are properties of these numbers that result in a proof. And I'm not sure, at the end of the day, if the Smt solver needs to, it will try every possible combination and try every possible value of X and solve it. When we get into that situation, we often see that the Smt solver doesn't come back, and we end up waiting forever. And that's sort of the bane of the proof engineer's existence when that happens. So that's this is the really the meat of what we do from day to day. Does that answer the question reasonably well?
Yeah. I mean, that gives me an idea. Great.
The upside to this is that there is this degree of automation, right? When we get some of these proofs to work, the Smt solver is reasonably flexible. So there are code changes that will not necessarily result in the proof needing to change. Things like reordering instructions, which is a pretty common thing we see in x86. Maybe we swap around the order of some instructions to make better use of registers, for example. Won't necessarily cause a need for the proof to change. More complicated mathematical things, we've had mixed success with the prover coming up with results. And of course, once things get into the degree of like, we had to write a paper to explain this optimization, the Smt solvers are going to be unable to deal with that out of the box. So
I mean, in this particular case, it looks as that if you do split it into 32 bits, then the problem's going to be almost trivial because you're just moving the bits around. Oh, there are some additions as well, and those don't commute with the ands, but that's probably okay.
Yeah, I believe that's.
Yeah, but the additions are on disjoint bits, so it's going to be fine. Okay.
Yeah. And just to give you a sense of what things look like, yeah, we have this example of one that we've broken in a very specific case, and all that we do, so we can apply this exact same spec to pop spec. Let's see, we call it. So here we have this particular broken implementation, and we can see that we have this we have a failure, and so in this case it tells us that we have this post condition. You can get a little insight into what the internal representation of SAW looks like here. We provide this for debugging purposes, and in this case, what the actual useful information is that it actually spits out a value for which the property that we expected doesn't hold. And so you can use this to trace back through the program and figure out what actually went wrong. In general, we spend more time debugging in these formulas, I believe. But for simple challenges, the counterexamples are quite useful. So we have one more example, which is going to show how we use this language Kryptol we mentioned. Kryptol, again, is the specification language that we use. We like to use it to write down cryptography, but it can be used for quite a range of other things. And so the problem that we have here is that we have this min-max function. And what min-max does is it takes in 2 pointers to 64-bit integers, and it figures out which of the two is larger. And so if X is greater than Y, we basically do a swap. So we want Y to point to the larger at the end of the day, and we return 1. Otherwise, we return the negation of X is not equal to Y. So we return 0 otherwise, it looks like. Or -1, I would say. -1. So in this case, we also write a Kryptol spec. So we have. So this is a different programming language. It's a functional programming language called this is Kryptol. One of the really important things about Kryptol is that it lets you, in the type system, it lets you specify the length of sequences. So here we actually define min-max as a function from a pair of sequences of 64 bits, basically, into a pair of sequences of 64. And basically we say if X is greater than Y, then we return YX, otherwise we return XY. We also specify the return separately. And so we say, we write down a specification for both of these things. SAW can import that file directly. So SAW sort of is built with an understanding of Kryptol. And then we do the same kind of thing. So here we have to do things a little more complicated because we have pointers. And so this is a roll.dot function that says we have allocated data, and that points to this symbolic variable that we're going to call Y. That's a 64-bit. X, excuse me, in this case. And then we do the same thing for Y. So we allocate data and we point Y to that. Then again, we call our function with these pointers instead of the actual values. And at the end of the day, we say that we are going to use this min-max function. So here we're actually referring to this Kryptol function that we use to specify the result. And we say that X points to the 0th thing. So if you recall, we were returning basically a tuple here. That tuple can be indexed in 2 with the 0 and 1. So when we talk about the 0th index, we're talking about this first variable that we use to represent the X result. And when we talk about 1, we're using the 1 variable that we use to talk about the Y result. So when we use a points to afterwards, we're saying that the result has these properties. And we're also able to specify the return spec. So the overall meaning of this, if you're not familiar with the idea of a Hoare triple, this is actually a Hoare triple. The idea of a Hoare triple is to have preconditions and postconditions on a function. And the meaning overall there is saying, we say, if the precondition holds on the variables that I pass in, and in this case, the precondition is fully general. We say for all values of X and Y, basically. If the precondition holds, and then I execute my function, then the postcondition will hold. So there's one thing to notice here, which is that we actually do get to narrow down the precondition. That means that formal verification isn't necessarily by default fully general. We don't have to prove this for all possible values. In a simple case, we do prove it for all possible values, but in general, that's not a requirement.
I noticed that the test doesn't cover the case where X and Y are pointing to the same memory.
Yeah, that's a great point. In those cases, we do need to write separate specifications. So we don't have a way to write those all in the same spec. But yes, we do refer to these as 2 separate allocations. This is a challenge that we run into often, in particular, when we deal with big num operations, where big num library implementers love to provide these at all possible aliasing combinations. And so often we do sort of end up in a spot where we have to write lots of different specs. Mark or Giuliano could confirm whether that was the case. That's been the case for BLAST. I see Mark smiling, so I suspect it is. Yeah, so we write separate implementations, and of course these are checked at the caller side, right? So when we talk about a function used internally in the library, if we prove the wrong thing, if we prove with too narrow of a precondition, and then we try to prove a caller that's using it outside of that function, the tool will complain. So Giuliano will get into a little bit of what compositional proof looks like and how we do that, but SAW lets us have this ability to build smaller proofs as building blocks in the same way you build your code, basically, and to combine those to build an overall proof of an API function at the end of the day.
So in this case, would it keep track of the fact that you've assumed that X and Y are distinct pointers, or do you have to keep track of that manually?
It will keep track of that, and so this is getting a little ahead. We have this empty list here, and what we provide in this empty list, when it's not empty, is a list of the functions that we might, the specifications that we might need to use in the process of proving this function. And one capability that SAW has is that you can provide it with even a bunch of specs for the same function, only one of which might match at any given time. And SAW will try out all of those specs and use the one that matches. So if, for example, a function uses, sometimes uses the aliased version and sometimes uses the non-aliased version, we can simply supply those separately and SAW will figure out which one to use at the appropriate time based on which one matches. Yeah, and so in this case, we have a bunch of different implementations of min-max again. They're all sort of straightforward and right, and we can prove those. The real purpose of this was to show that we can use Kryptol in these specs, because once I hand it off to Giuliano and Mark, they're going to talk about a much more detailed use of this, and also to show that we can deal with pointers, and it's also served as a nice lead into compositional proof.
I noticed that min-max XOR wouldn't actually work when the pointers are the same, whereas the previous one with temp would.
This XOR one would not work.
Yeah, this is a well-known problem with the XOR. It's why you one reason why not to use it.
Yeah, and the great news is, again, if we proved, so this is already, when I said this was the fully general version, you correctly called it out as not being the fully general version. And again, if we tried to prove a caller that was calling any of these with the same version, it would complain. Again, this speaks to the point. It's some point where formal verification is never sort of the final answer. Nothing's ever the final answer in code correctness. Formal verification is about as close as you can get in a lot of cases. But at the end of the day, there's still this critical thing where we need to understand the specifications in order to really understand what the formal verification is saying. The one thing to note is that there's this view of the external and the internal, right? Once we've done this proof, if it's an internal function, if it's something that a user never calls, we actually don't have to worry about it that much. This is because of this property where we've checked all of the callers of this proof and they match up to the way that we've proved this function. And so at the end of the day, we can sort of abstract over all of these detailed internal proofs, and we can provide the API functions as the real point for understanding. It's not always that simple, because sometimes there's a lot of meaningful stuff going on in the internal versions. But at the end of the day, if you can believe the external spec, and if that seems like the right thing, then that's really what you care about. And only if you do sort of personally find this need to dive into the internal specs to get more of an understanding of going on, do they matter. So this is again about pushing the correctness needs out to well-defined boundaries, is all of what we're trying to do. Great. So that's been the simple demo. Of course, nothing is this easy. When we talk about verifying something as complicated as BLAST with all of its with all of its optimizations and just how hard the problems that it's trying to solve in general are. So I'm going to hand it off now to Giuliano, who will take you through, I believe, how we're representing the numbers that BLAST use, and maybe then Mark will take us through some of the curve operations.
Yeah, thanks, Joey. Yeah, so for BLAST, of course, we're faced with significantly more complex code than what you've just seen, and there's a lot to say about how we do it. But so here I'm just going to try to give you an idea of so one aspect of it, which is a prerequisite to understanding the rest of the proofs, and so it has to do with how we treat and abstract over concrete data and algorithms used by the C code. So let me try to present. So I'm getting host disabled screen sharing.
May need to make you a co-host here. Joey, I don't know if you have that capability. Oh, there you go. Should have access now.
All right.
Did you make Mark the co-host or Giuliano the co-host?
Looks like they're both the co-hosts now.
Okay.
Okay, is it working now?
Yeah, looks great.
Great. Okay, so so in the case of BLST, yeah, so as I was saying, we have significantly more complex code, and so what happens is that we get a specification and code which become quite different, because in the specification, which we write in Kryptol, we want to make the meaning of the code as clear as possible. So for that, we work more in the mathematical realm, where we specify things. For example, in the case of the field FP used in BLST, we specify elements as mathematical integers and not bit vectors or anything like that. And then when we specify what operations on those field elements should do, again, we use high-level mathematical operations, so integer multiplication, the bound-to operator, or in the case of division, we define division using the extended GCD algorithm. Now, if we look at the code doesn't really look like that at all, because it's not optimized for conveying clear meaning and explaining things. It's optimized for security, side channel attack resistance, and speed. And so it's not going to use arbitrary precision mathematical integers, obviously. And what we see in the code is that an element of the field FP is represented as an array of 6 limbs of 64 bits each in little endian representation, and it's also encoded in Montgomery form for efficiency of operations. And then the operations themselves, they're implemented in assembly, in this case, following very optimized algorithms that are not the same as in the specification. Okay, and so now we need to establish relationships between those two worlds to prove that the code is equivalent to the specification. So I'm going to quickly go over how we do this. Okay, so let's take an example, the multiplication. So here you have a few lines of code taken from BLST, where we see the declaration of the function null FP, which takes 3 parameters. The first one will contain the return value after the call, and then A and B, the second and third, are the things we're multiplying. And you see above the declarations that define the representation of this vec384 type. So 6 limbs in little endian and it's actually encoded in Montgomery form. All right. So here's a diagram of how we use abstraction and representation functions to relate the specification to this code. So if you start by looking at the bottom of the slide on the left, so we start with two variables, x and y, that we want to multiply. So as I said, those are each 6 limbs in little endian in Montgomery representation. And going to the right, if we make a call to mul fp, then we get the multiplication of x and y in the variable in the memory allocation 22 by ret. Now, in the specification on the top, we were just using the abstract operation fp.mul defined in Kryptol, which takes 2 mathematical integers as input. So we're going to define an abstraction function that maps our concrete x and y to 2 integers. This function is called fp_abs. And then use the fp_mul defined in Kryptol to obtain the result of the operation in terms of mathematical integers. This is top right. And then use our representation function to map this back to the low-level representation, and then assert that the return value, which is pointed to by ret, is equal to the representation of the abstract operation applied to the abstraction of the inputs. And so this is what it will mean for this multiplication function to be correct on the bottom right. It has to satisfy this equation. Does that make sense? Any questions about that?
So this assumes full reduction rather than partial reduction, right? So there's you can't use a redundant representation of the.
That's right.
Integer. Okay.
Yes. But
you could generalize it to support that.
Yeah, we'll see that in a minute. Actually, what happens if you have to. So yeah, here I'm assuming that we have a kind of bijection between the concrete and abstract domain.
Okay.
Okay, and so this is what it looks like in Kryptol. This is the definition of the abstraction function. So we defined the type of limbs as a sequence of 64 bits, and then we define the first function vext284abs, which converts the 6 limbs into a big bit vector. And so since the limbs are in little endian order, we first reverse them and then we join everything. So we get a big bit vector. And oops, I'm sorry. Then we have the function 2fp, which takes this bit vector and converts it into a mathematical integer in Kryptol. Third line, we have now that we have a mathematical integer, we need to convert it back from Montgomery representation to just plain representation. So we have this function that just multiplies our number by the inverse of the Montgomery coefficient, which is 2 to the 384 in this case. And then finally, putting this all together, we chain all those transformations together to get our abstraction function. So which takes us from 6 limbs to a mathematical integer. All right. And so finally,
what was the reason for doing the 2 to the 4 times 2 to the 30 at 380 there?
Yeah, that's a good question. It looks a little strange.
I can speak. I can speak to that. That's a bit of an artifact. In the early stages, we were playing around with 3 different ways to do the abstract representation. And in one of those ways, if I'd written 2 to the 384, that would not have worked correctly because I was using 384-bit numbers. That just would have gone down to 0. I was using bit vectors. So this was a way of just expressing that would work in all of the 3 different ways that I was thinking of doing it. It's certainly no longer necessary in the way we're doing things, but it's not incorrect, so we just left it. And still gives us the ability, if we need to play around with the abstract representation.
Okay, thanks.
Okay, thanks, Mark. So now that we have all the pieces here, you can see the full SAW specification of the molFP function, which combines the specification about the value it should return that we've just seen with also memory layout information. So the first 4 lines describe what the memory should look like when we call this function. So second line says that the return should just be an allocated piece of memory. It doesn't have to be initialized or anything. And then, but X and Y should be here pointers to initialized location of there are arrays of 6 limbs of 64 bits. Now, line 5, we also additionally require that whenever this function is called, then X and Y should satisfy some invariant. And this invariant is that the value encoded in X and Y are smaller than our prime P, which defines the field. So line 6, we make the call to the function. And then finally, last line, we assert that after the call, what we find pointed to by red is described by the Kryptol specification that we just talked about. So if I take the abstraction of the 2 inputs and then I apply the abstract definition of multiplication, and then finally I concretize again with FP-rep, then I should find the value that's pointed to by red. Any questions about this? Okay, and so a lot of the specs we write for this proof are going to be in this style. Now, sometimes, as I forgot who made the comment, sometimes it doesn't work as simply if there's no bijection between the abstract domain and the concrete domain. And so this will be the case, for example, when we talk about not just field elements, but also points on the curves. So here, for example, the curve E1, it will be the same problem for E2. So the issue is that in the specification, we use affine coordinates to describe the operations, because that's the simplest way to do it, and that's the simplest definition that make it easy to inspect and see that the definition is really what we want. But the code uses projective coordinates for efficiency reasons. So in affine coordinates, a point is just 2 coordinates x and y, but in projective coordinates, it's actually 3 points x, y, and z. And the relation between the 2 we define, as you can see at the bottom of the slide. So if I get a projective point x, y, z, its affine counterpart is defined as you see here. So if z is 0, then it's the point at infinity, and otherwise it's defined as x over z square for the first coordinate and x over z third for the second. And then to projectify, we just set z to 1. So now if we try to do what we've done just before, we're going to have a problem. So just briefly, so we start at the bottom left with the concrete representation. So we have 3 coordinates, each are 6 limbs of a Lagrangian in Montgomery representation. And we take the example here of point doubling. So we call the point double function, and we want to specify what the return should be. So we can do like before, we abstract two this time pairs of integers in affine coordinates. We apply the abstract operation, and then we concretize again. So does anybody have an idea of what the problem will be here? So as somebody pointed out before, there's no bijection between abstract and concrete domain here, and in particular, as we've seen, we use the definition of projectify, the result must have z equals 1, which there's no reason the implementation would produce a point with z equals 1, because that would defeat the whole purpose of using projective coordinates for speed. So this is obviously not going to work. So instead,
I'm not even sure that that projectify definition will work for the pointers to infinity if you're using xy equals 0, 0 as the affine representation of the pointers to infinity. You would normally use xy 0 as the projective representation.
That's correct. Yeah. So we might have a special case for this.
Yeah. We're simplifying just a little bit here, but
yeah,
that is correct observation.
Yeah, you wouldn't get to that problem because you've got this problem first.
Yeah. But yeah, anyway, so we if we made projectify right for 0, what we could do is do it like this, where instead of saying what the concrete return should be, we can compare things at the abstract level. So the equation now is appearing at the top right, where we say that the specification is that if I abstract the return, then I get the same thing as what the abstract operation computed given the abstracted inputs. Okay, so if that makes sense and there's no questions, I'm going to let Mark show you some code related to that, and he'll probably be able to give all more concrete details.
Okay, yeah, I'll take it on then. Yeah, so this is the plan. So we've got these two kind of approaches that we use for writing the specifications. We either try to keep a very concrete form where we say the return value equals some exact thing, where we use a representation function, or we might have to boost up to the abstract realm. And it turns out for most of what we're doing, it's, in the course of the proofs, it's far more convenient to keep things, use that first method if possible. And so I'll get just share here, and I'll show you what this is looking like. There we go. Okay. Okay, is that visible and legible?
Yep, looks good.
Okay, all right, so yeah, abstraction representation. So yeah, when we were deciding what to show, everything that we have is a little bit messy, and there's this clear plan of how it should work, but nothing that we've done exactly corresponds in every detail to the plan. And the curve operation here is no different. Anyway, the way the proof looks here is, and I'll go through these bits of code later. We do have Kryptol specs then for the elliptic curve operations in affine coordinates. We then, as part of the proofs, we wrote then some more implementation-oriented Kryptol definitions. And as well, we wrote some Kryptol definitions that very closely mirror what the blst code does, which makes the code proof quite simple. And then at a separate step, it's a simpler proof then to show that those two Kryptol definitions are equivalent, or at least they're closely related. And then we can have another proof that shows that these lower level things are consistent with the very high level and more elegant specifications. And then we've got several options having proved those three things, one of which is the theorem that the kind of specification Juliana just mentioned, where in the post condition we say now the abstract value is correct. And We have done that for things like scalar multiplication, where that was the best way to go. But for the curve operations, and where they're just being used internally, it's actually a little more convenient for us to have a post condition that sticks with one of these slightly lower level things, so we can talk about what exactly we're representing. Now we're a little short on time, so I'll go right to the code examples here. Right to the code examples. So just to give a little flavor of what these things look like, I'll just run through the files a bit. So what does a Kryptol look like? We have some very high level things to describe, here's the prime fields we've got with some basic functions and building up the field tower. A lot of functions, and then other things that define what our curve parameters are. And these are, except for the fact that they're using hex, these are fairly mathematical, and it's all just in terms of integers and field values. More Kryptol here that talks about elliptic curves in affine coordinates, and what the various operations for telling if two projective representations are the same point, and definitions of some of the operations. There's adding, for example, where you have to look at all these special cases where the normal formula doesn't work, or else you use the raw adding formula. Anyway, just things you could get out of a textbook on elliptic curves. We have some more implementation-oriented code here. So for fields, here's the part where we describe how we are doing the representation. Juliana already showed you most of this, where we managed to go from this implementation type. This is being the Kryptol representation of the 6 limbs up to our abstract integer type that we use. And this goes on for a while because we've got, of course, FP, there's FP2. In our mathematical specification, this is described just as a polynomial quotient ring, as you would normally do that again in a math book. Then you can see the representation function here. It just so happened that the polynomial ring representation was big endian. It goes, coefficient of x squared, x, and go down to the constant coefficient, whereas the code goes the other way, and so we have to deal with the reversal here. And there are other fields and rings that are involved, and they're all defined here, going up to FP12. Right, the code we're looking at is generated by these macros. So the C code, this is now the blst code. There's a instantiation of this macro that creates the code that gets compiled down to SAW script that we are analyzing. So there's the double code. We did another implementation level specification of the elliptic curve operations, this time in projective coordinates. So this was not part of the original high-level specification of BLST that said what the types were, what the curves were, what the operations were. Those were all being done in terms of just affine curves over integers. Here we've got projective points, which we can either affinify and map to affine coordinates or map up to projective coordinates in integers. So we have this, again, representation invariant, but the 3 coordinates should all be proper representations of field values. That's for both curves, for E1 and E2, similar things. There's a version of the algorithm written down here in Kryptol, which corresponds pretty closely to the code that we're seeing in BLAST. And down here somewhere there are some other definitions which now come from the literature. So these are published algorithms rather than the ones which are in the code. These are algorithms which we trust working in projective coordinates, which do correspond pretty well to what the code is doing. And we are going to show a couple of things. We're going to show that the algorithm as implemented in the code agrees with this algorithm out of the literature. We actually have an algebraic assumption, something we're not proving at the moment, which says that this algorithm does the correct thing when you affinify, does the correct thing in affine space. And well, and that's that actually. That is that.
So a common technique in, say, scalar multiplication is to use incomplete additions because you can prove that the special cases don't occur. Does BLAST use that technique, or do you have to then prove?
Yes, there are places where it.
Okay.
Yes, that came up in scalar multiplication, where in scalar multiplication, there's sometimes you're adding, well, you're some multiple of p and then one higher multiple of p, something like that. And you know they're not, if they are equal, they're both zero and it's going to work anyway. And so there are cases where you can do that. And yes, we did those proofs that showed it was legitimate to do it in those cases. Sometimes that just gets pushed up. We say this routine will only work if you call it in certain circumstances, if you call it with points that have sufficiently large order. And you know, the proof that all the points in this subgroup have order R is something we're not mechanizing. We're just, again, going to assume that's a given mathematical fact.
I see, okay.
Yeah. Okay, so down to what we do here. So now I'll show you some of the SAW script code, the input that we are giving to the tool to finish off the proof. So as mentioned, there are a couple parts to it. One here is a theorem just about the Kryptol functions that we've defined. So this point double, that is the Kryptol function that corresponds pretty directly to the code. And this other one over here is from the literature, a point doubling. It's well known. And that's just a trivial proof. We just send it to the prover, and the prover is able to show those algorithms give the same answer, which is good. I think that's a relic of an earlier written out proof. Well, here is a specification, actually two specifications, depending on how we set this Boolean of the double function. So again, we have just an allocation of free space for the result to sit. We have an input, which is a representation of a point, and we are assuming that that is a well-formed input here. And then we just make the call with these two things. And then, well, we had two different ways of doing it. And this was at an early stage where we were still playing around with different approaches. But the one that's being used to write a representation of this point doubling. So this Kryptol function where, you know, we're not worrying in the Kryptol function about big Endian representations or how you represent big nums. We're just doing integer operations, and we're showing that the code has correctly done that. And then this command here actually makes the proof happen, where we ask to verify this function with respect to this specification. The overrides relate to the compositional proof. So here's a list of all the things that we're assuming. We've got some specifications that we proved for the vector functions and for the functions that work on field elements. And we also have a number of rewrite rules that we've written to simplify those formulas a little bit. And well, you can run it in SAW. It's not all that informative to see, but if you do, you see it actually applies all these overrides, and it runs the proof script and succeeds. It's not very exciting when it succeeds, but
how often do you have to sort of do this kind of manual proof engineering rather than just the automatic proof set?
The proof engineering occurs a lot in BLST. Some of it has to do with the Montgomery representation. If we just open everything up, then we get these very nonlinear terms. They've got this constant multiplication and modular reduction everywhere. The Smt solvers don't really deal well with that. But as you saw earlier, the Kryptol level proof was all just at the integer level. that you could just tell the prover to blast at it and it would go. And a lot actually of the algebraic proofs, when they're just about numbers, they work fine. For the code proofs, we typically have to be a little more careful and picky. So yeah, that's just how it is, and it's somewhat painful, but it's, well, yes, it's somewhat painful.
Thanks.
Anyway, another thing, so that is the main double override. We also have another specification here for an aliased call. So in this case, there's only one pointer because the same pointer is used as both arguments. So it has to come in initialized, and we just say in the end, or in the end here, that pointer points to, again, this correct term. It's been doubled. And in, for example, in that scalar multiplication proof, we need to use both these overrides because both the cases come up. And the simulator, as it's going through, it figures out which one to use and makes that all happen. So in this case, yeah, these more abstract post conditions, we can prove them. And for many of the callers of these, we end up proving these more abstract post conditions. But it turns out at an intermediate level, when we're using these overrides in the course of other proofs, it's much better to work with these slightly lower level post conditions. And at the very end, we just, at the theorem proving level, we just use these theorems that we've proven to eliminate them all. So there were a couple other interesting points. Back to
we're a bit past time, so I think we can go on for a few minutes longer. No hard feelings, of course, if you have something else and need to leave. But if you,
okay, yeah.
If you want to stick around for a few more minutes while Mark wraps up, you're welcome to as well.
Okay, yeah, I'm pretty much done here. Just wanted to mention the algebraic assumptions. That's all. That's the last thing I wanted to say. One of the assumptions we make related to the curves is that these algorithms, these well-known published algorithms, do the correct thing. It's not that we couldn't prove them, but that's already been done. If you look at, say, hyperelliptic.org, they have some code for validating all of these in a computer algebra system. So we don't think it would be a productive use of our time to reprove these things here. We're just trying to get all the other proofs done, and we will document all of these algebraic assumptions we're making at the very end of it. And these things, yeah, they can be manually reviewed.
Can you give an example of an algebraic assumption?
Well, there would be this one right here, for example, that says that. We have some other ones that related to Montgomery representation. There is one that says if you just multiply two numbers that are in Montgomery representation and then you divide through by the constant, you end up with the Montgomery representation of the product. That's something that we haven't proved. We've just, it's a well-known thing. It's easy to do on paper. It'll be similar for the Montgomery reduction if we get to that assembly language proof. That's in several papers. It's been mechanically verified some other times already, and so I don't think it's the most productive use of our time. It's not where your mistakes are going to be, if there are mistakes.
And as a result of this verification, one of the things that we'll do is publish all those plainly and point to them. The point here is that these aren't meant to be, we're not trying to hide anything under the rug. There's always things that you can't prove. And at the end of the day, that one of our goals is to explain what we can't and didn't prove, so that manual inspection can help fill in the holes. Because with any formal verification effort, you do need to evaluate it and understand it. And so we're really trying to define that clearly, so that anybody that's interested can see for themselves, basically.
Has there been any bugs or otherwise problems found in BLAST as a result of this work?
I think there have been some light fixes. I don't know if there's anything we would go so far as to call a bug. One of the things to think about with regards to formal verification is that Supranational has been treating this appropriately as part of, a many-layered approach to showing the correctness of the library. So we would never recommend formal verification as a first step. In fact, if you're finding a lot of bugs with formal verification, you've probably made a mistake in going for formal verification. because you would find more quicker with things like fuzzing, which we've seen applied to BLAST, things like independent cryptographic review. So there was an NCC group review of BLAST as well. There are a lot of things you can do quicker to find bugs. And the way we think about formal verification is really to iron out the very last things, or, if you've done a good job, to show that you've done a good job so that everybody can understand the shape of things. So the answer to your question is not really. It's been minor details. And, again, if we expected to find a lot of bugs, can anybody else hear me?
No, yeah, I can hear you fine, Joey. I think maybe that's yeah, Dongrad may be an issue on your end, but I can type with them.
Yeah, if somebody reached out to us on a code base where we looked at it and we said we'd expect to find a lot of bugs, then we would probably recommend starting somewhere else first. So for example, we've done a lot of testing applications to cryptographic libraries, things like BKCS11, big cryptographic providers. And we would never start to verify those. We try to apply testing broadly. And once you gain confidence, once you understand where your trouble spots are, then you can go on to verification. But we would, we like viewing these things as holistic. Fuzzing, for example, can help, even if we mentioned these cases like the compiler tool chain isn't working right. Testing might catch that, whereas verification might not. So it's always a holistic view of library and program correctness, and we would never say that verification should be the only thing you're doing at the end of the day. Thanks for that question. Any other questions? Great. Thanks for joining us. Feel free to follow up by email, Twitter, whatever you're interested in. I think we've recorded this and we'll likely post it. So if you have any, if you need to review anything later, or if you find this useful, we'll make sure to share that out once we're done.
Yeah, thanks again, Joey, Mark, and Giuliano. And as Joey mentioned, I think for those of you that have a calendar invite, if you have suggestions or things that you'd like to dive deeper on in maybe a next workshop, please let us know, and we'd be happy to sort of entertain those and figure out how best to communicate some more of this, more on the topic.
Yeah, by request, we'd be thrilled to come back again if anybody sort of, especially as we get into what Mark was starting to show, if anybody wants to see more detail of what the actual proofs look like, I think that would be worthwhile, assuming that there's interest. So
fantastic. Yeah, and a special thanks to everyone that joined today, and once again to Ethereum Foundation and Protocol Labs for sponsoring this work.
Great.
Thanks, everyone. Have a great day.
Yeah, bye.